Lesson 2.7, Proving Segment Relationships. In this lesson, we'll explain the difference between the reflexive, symmetric, and transitive properties and use them in proofs. We'll also explain the segment addition postulate and use it in a proof. Let's get started. In our last lesson, we examined algebraic proofs, where we focused on something really familiar to us, properties of equality. In algebra, we're talking about numeric values or variables that would be equal to each other. Today, we're going to combine properties of equality as we talk about measures. Measures are numbers that would be equal. We're going to combine properties of equality and properties of congruence. Remember, congruence is about shapes. Shapes aren't congruent. Shapes aren't equal. Shapes are congruent. We always have to keep that in mind in geometry. And we're going to use those properties of equality and properties of congruence to prove segment relationships, relationships that we'll see all year long in our proofs. Now, there are some properties of equality that have corresponding properties of congruence, but not all of them do. We'll just have to get used to it as you practice more and more. So let's look at some properties of equality that do have a corresponding property of congruence. First off, we have the reflexive properties of equality and congruence. Remember, properties of equality are about measures. So if I'm talking about segment lengths, remember the notation for segment lengths does not include the bar. This refers to the measure of segment AB. And if I'm talking about the reflexive property, I can say the measure of AB is equal to the measure of AB. In other words, the value of anything is equal to itself. The same could be said of shapes. I can say that the shape of segment AB is congruent to the shape of segment AB. So the reflexive property of equality says that any line segment is congruent to itself. So any measure or any shape is equal to and congruent to itself. That's the reflexive property of equality. And I know it seems really obvious, but we're going to call on that a lot in proofs in chapters to come. The next property that has both an equals version and a congruence version is the symmetric property. The symmetric property says, the symmetric property of equality says that if the measure of segment AB is equal to the measure of segment CD, then the measure of segment CD is equal to the measure of segment AB. That's the reflexive property. You can see it's almost like looking in a mirror. So here AB equals CD and CD equals AB. Correspondingly, we have the symmetric property of congruence that says the same thing except with shapes and congruence. If segment AB, not its measure, but the segment itself, is congruent to segment CD, then the reverse is true as well. Segment CD is congruent to segment AB. I'll just reiterate that measures are equal, shapes are congruent, and the order in which things are equal or congruent doesn't matter. And finally, we have a transitive property of equality and a transitive property of congruence. The transitive property of equality says that if the measure of segment AB is equal to the measure of segment CD, and the measure of segment CD is equal to the measure of segment EF, you'll notice that we have some connective tissue between these two equations. Both of them are equal to the same value, CD, whatever that measure is. So if AB is equal to CD, and the measure of CD is equal to the measure of EF, then I can say that the measure of AB is equal to the measure of EF. And I'm going to write the same thing for congruence and talk about shapes. If segment AB is congruent to segment CD, and segment CD is congruent to segment EF, oops, that a little funny, then segment AB is congruent to segment EF. Again, if they're congruent to the same thing, they're congruent to each other. Let's go ahead and write that much down. If two things are equal to or congruent to the same thing, then they are equal or congruent to each other. So those are the reflexive, symmetric, and transitive properties. We have properties of equality and properties of congruence for each of those. But like I said earlier, some properties of equality don't have any corresponding properties of congruence. In our last lesson, for example, we talked about the properties of addition and subtraction and multiplication and division, and the substitution property of equality. Those can only be used with numbers or measurements, not shapes. So I can't say triangle plus triangle. I can't add two triangles together and get anywhere. So if we're talking about numbers and values, these properties that we use for algebraic proofs only work with those. Let's take a quick look at a little proof that's in your textbook that proves the transitive property of congruence. Now, they use the transitive property of equality to do that, but let's just take a look. So if we're given this information that segment AB is congruent to segment CD, and segment CD is congruent to segment EF, we can use a property of equality to prove that segment AB is congruent to segment EF. Again, we're just proving that transitive property of congruence. We're going to use a little paragraph proof here. It's kind of like a two-column proof, but it's just, writing it out as a narration instead of statements and reasons. So by our reasoning, since segment AB is congruent to segment CD, that was given to us, and segment CD is congruent to segment EF, that was given to us, I know that AB equals CD and CD equals EF by the definition of congruent statements. So here we just moved from what we were given about their congruence to what we're allowed to say by this definition of congruent segments. The definition of congruent segments says that if I have congruent segments, then the measures of those segments are equal. So we just shifted from congruent segments to equal measures. And apparently we can use that transitive property of equality and say then that AB is equal to EF. So again, going in the other direction by the definition of congruence, if the measures are equal, then the segments are congruent by the definition of congruence. So that's what we were asked to prove, that segment AB was congruent to segment EF. And there was just a paragraph to explain why that is true based on the transitive property of equality. Let's flip over. One of the things in our learning targets is to talk about the segment addition postulate. It's another one that we'll be using all year. Let's take a look at what it says. The segment addition postulate says, if A, B, and C are collinear, then point B is between A and C if and only if the measures of these two smaller segments add together to be equal to the measure of the whole segment. That's what the segment addition postulate says. I want to take a look at this if and only if wording. There's a symbol for that. And it means this statement is going to go both ways. If these are collinear, then B is between A and C, if and only if that equation is true. And it goes the other way as well. If that measure plus that measure equals the whole segment, then I can say that point B is between A and C, and that A, B, and C are collinear. So we're going to use this segment addition postulate in this overlapping segments theorem. I know it's hard to get used to proofs, so I just want you to watch and play along and anticipate some of the things that are going to show up as we talk through. So let's look at what we're given in this figure and what we need to prove about this figure. What we're given is that segment AB is congruent to segment CD. I'm just going to mark those with slash marks to indicate that those two little segments are congruent. And what we're asked to prove is that segment AC is congruent to segment BD. So with any good proof, it's probably wise to just go ahead and begin with what's given. So I'll let that be my first statement. Segment AB is congruent to segment CD. And I have to give a reason that I'm allowed to say that statement is true. And in this case, it's given. Now, I'm telling you, I'm going to be using the segment addition postulate from up above, which is about an equation. I like this equation up here. And if I'm going to use an equation, then I have to shift from talking about segments to talking about measures. So I'm going to go ahead and switch from talking about these segments being congruent to the measures being equal. We have to do that a lot anytime we're going to slip into an algebraic proof and we're dealing with equal equations. So can you remember what the reason is that we're allowed to say that? We'll be using the definition of congruence a lot. It will get us from talking about congruent segments to equal measures and from equal measures to congruent segments. Okay, well now we've got these two measurements that are equal. And we have this third segment here, BC, that's in between them. And I know that it's equal to itself. We'll look at how we can use that fact in our next step. But maybe you can remember which one of those properties that we talked about on the flip side is when something is equal to itself. I can say that from the reflexive, that's an R. I'm going to write POE for property of equality. All right. And now we're going to go back to what we know about some algebraic facts. If I add the same value to both sides of an equation, then the resulting equation is true. So I'm going to take the equation from step 2 and add this value to each side. So AB plus BC. And then on the right side, I'm going to take this CD and add the same value. Maybe you can remember that what I've done is I've added the same value to both sides of an equation. That's the addition property of equality. And here's where we're going to be using the segment addition postulate. So I know that AB plus BC in this figure has to be equal to AC. Again, this segment plus BC would be equal to that whole segment from A to C. And I'm going to use the same reasoning with BC plus CD is going to be equal to that whole segment between B and D. Right? That was just the segment addition postulate. Now let's take a look at what we've really done here. We have AB plus BC, and we have CD plus BC. Now we know that AB plus BC is AC, and CD plus BC is BD. So let's look at how we can pull all of that together. If AB plus BC is equal to AC, then I can substitute AC wherever I see AB plus BC. And the same is true here. CD plus BC, kind of flipped around here, is equal to BD. So I can substitute BD wherever I see BC plus CD. So let me go ahead and do some substitution now. I'm going to substitute AC in to this equation, or to this expression. And I'm going to substitute BD in for this expression. It's our substitution property of equality. I just substituted in a segment measure for this expression. POE for property of equality. I'm still dealing with equal signs. And I'm almost there. So just so we're clear, what I've done so far is I started by changing congruence to equality. I set up some equations where I could substitute in and get super close to what I wanted. I want to say that segment AC is congruent to segment BD. And I've got the measure of AC is equal to the measure of BD. So hopefully you can see the one last little step that I need to take to get step 6 to look like this. All I have to do is go ahead and get to that final statement. And the reason that allows me to go from that to that is the definition of congruence again. So we wanted to use the segment addition postulate, and that's what we did right here. All right. The more proofs you look at, the more used to them you're going to get. I know that it all seems brand new right now, but there's little cycles of little steps that show up again and again and again. But we have to get to the again and again before it feels comfortable. Oops, I got that backwards. In the end here, I moved from equality to congruence. A couple of quick reminders before we finish. The definition of congruence says that congruent segments have the same measure. We used that a couple of times up top. And you might need the midpoint definition. The midpoint definition says that if M is the midpoint of segment AB, then the measure of AM is equal to the measure of MB. And it also means that segment AM is congruent to segment MB. So in this lesson, we explained the difference between reflexive, symmetric, and transitive properties, and we used them in a proof along with the segment addition postulate, which we explained and used in a proof as well.